Alright guys, so we're going to see how this works. I've previously recorded this and realized I only get 30 minutes of recording on the app I'm using, so I'm going to do this in a lesson breakdown. So I think the first recording I'm going to do lessons 1 and 2, then I'll stop, then I'll go do lessons 3 and 4, I'll stop, and then I'll do lesson 5, so it'll be 3-part videos, hopefully not very long, and then I will post the blank notes for you guys on Google Classroom along with the videos all like in one chunk. This is kind of just to be like a breakdown and answer. I have answer keys for the PDFs, other worksheets, not the multiple choice, that I will post for you guys as well. So let's get through lesson 1 and 2, just brief overview, and then we'll move on from there. All right, so lesson 1 was collision theory and factors affecting reaction rate. So kinetics, that's what we're studying right now. The first part is kinetics. The second half is equilibrium. They kind of come together eventually. So kinetics is how fast or slow a reaction takes place. So the rate or the speed of a reaction. And throughout this whole thing, we're going to abbreviate reaction with RxN, just because it's easier and I'm not used to writing on the iPad yet. Just like I still can't write on a smartboard, but it's fine. So a reaction is the breaking and reforming of bonds. So breaking, reforming of bonds, that's big. In order for these reactions to occur and take place, we must have effective collision. So an effective collision is the way in which reactant particles collide. We have to collide at the right time. So at the right time and the right orientation in order, with the right energy. This little spot down here was supposed to be an animation, but it didn't show up in this app, so it's fine. We don't need it. So an effective collision is something, reactant particles colliding at the right time, the right orientation, and the right amount of energy. And there are 6 factors that can affect the reaction rate. So 6 factors that affect the reaction rate. And we're going to talk about each of these. I have 3 on each slide on the next 2 slides. So let's take a look at the first 3. So type of reaction. So here we're looking at whether the reaction is reactants are ionic or covalent. So ionics, remember it's a metal and a nonmetal. So let's say we had sodium chloride. This is going to break down into its ions, sodium plus Cl minus. So ionic compounds are going to move and react a lot faster than covalent compounds because of this ability to break down into ions very easily and very quickly. Covalent compounds take more energy and more time to break down from one another, so they're going to move a little bit slower. So our type of reactant, this first one, whether it's ionic or covalent, ionic compounds are always going to react faster than covalent compounds. So if you were to get a question like this, it would give you multiple choice question. It would have 4 choices, let's say, and each one would be 2 different reactants. If it's asking which one's going to react faster, you're going to look for the answer that has 2 ionic compounds in it. Ionic is faster than covalent. That's what you need to remember here. Our next one, let's change our color. So concentration. So remember these brackets equal concentration. So when we're increasing the concentration, we're increasing the quantity or the amount of particles. So when we have an increased concentration, we have more particles and more effective collisions, right? So we have our concentration of our solution, right? When we increase that concentration, we're putting more dots in here, right? So there's more opportunity for collisions to occur. If we go the other way and we take away or we decrease the concentration, we have less particles and less collisions, right? So let's have our beak over here. So this was our initial, and now we have less, right? So there's less opportunity for collisions to occur, and our reaction rate is going to go down. And let's pick our third color for temperature. So temperature, again, when we're increasing the temperature, we're increasing the reaction rate. So we can look at these all as direct relationships. Well, not all of them, I'm sorry. Concentration and temperature, we can look at a direct relationship, right? So as one goes up, the other goes up. One goes down, the other goes down. So with temperature, Again, when we increase the temperature, we increase the collisions, right? We're adding heat. These particles are now bouncing all over the place. They're moving so much faster, so the opportunity for a collision to occur is higher, right? Think about an ice cube, right? An ice cube is a solid. Are those particles bouncing around? No, and that's cold, right? But as we move through, we have liquid water, right? They're bouncing around, they're moving. And then we go further and we have water in the gaseous state, right? And this is usually hot because of evaporation. So these guys are moving around much faster. There's more opportunity for collisions to occur in a closed container, right? So reactant type, ionic, reacts faster than covalent. Concentration, increase reaction rate. Temperature, increase the reaction rate. So now let's look at pressure. Remember, anytime we're talking about pressure, we're looking at gases only. So when we're increasing the pressure, we're decreasing the volume, which in turn increases the concentration, right? And what did we just talk about from increasing concentration? It increases the reaction rate because those particles are now closer together in that tiny, tiny space that you just added pressure to. And they're reacting and they're colliding more. So increased pressure, increased collisions, but only for gases. Right? And then we have our surface area, right? This guy here. So when we increase the surface area, we increase the reaction rate. This is because we now have more particles exposed to react. So a fine powder will react quicker than a solid chunk, right? Ooh, I'm dropping things here. So if we had like powdered zinc or powdered magnesium versus a chunk of zinc or a chunk of magnesium, the powder is going to react so much faster. The solid chunk is still going to react, but will react a lot slower than the powder. And finally, we have a catalyst. So what a catalyst does is it increases the rate of reaction, right, by lowering the activation energy. We're going to talk about activation energy when we talk about potential energy diagrams. But what is important to note about a catalyst is it is not a reactant. It is not a reactant. It's not consumed during the reaction. The idea behind adding a catalyst is to make it move faster, right? So we want to speed up our reaction. We want to make it go from point A to point B so much quicker. But at the end of that reaction, you're still going to have the same amount of catalyst left because it's not used during the reaction. So just keep in mind that a catalyst is not a reactant. It's not used during the reaction, and it's still going to be there at the end, but it makes the reaction rate go faster, right? So concentration, pressure, surface area, temperature, and type of reactant. Those are our 6 factors, and a catalyst. Those are our 6 factors that affect the reaction rate. All right, let's look at lesson 2. And then after lesson 2, I'll break there, and then we'll move on to lesson 3 and 4 in another video. So, lesson 2, we're looking at energy changes. This is supposed to be an S, energy changes in chemical reactions. So first, we're going to look at entropy. Right? Entropy. We're going to look at this. So disorder of a system. We symbolize that with delta S. This is also chaos. We can refer this as chaos in a system. Not going to lie, guys. I wrote chaos, and for a minute I didn't think that was spelled right, but that's spelled right. So, chaos of a system. Disorder. Craziness. Particles bouncing all over the place. Which tells us that a solid is going to have the least amount of entropy, the least amount of disorder, right? Because they're all ordered. It has that defined shape. We think about our particle diagrams, right? Gas, most entropy. Bouncing all over the place, right? They can't be contained, gas particles. Gas particles are all around you. They're the oxygen you breathe, the nitrogen in the air, even tiny, tiny bits of water vapor that are around. So you need to know that solids, least amount of disorder, least amount of entropy. Gas, most amount of entropy, right? And most of our chemical reactions go toward lower energy and higher entropy, right? So we want that chaos, we want that disorder in a system, but we want it at low energy, so we're not wasting a lot of energy. So that's entropy. Now we're going to look at enthalpy, notice the difference. This is our delta H, or our heat of reaction. So remember, delta means change. So this is our net amount of heat energy that's lost or gained through a reaction. And we have our H of our products and our H of reaction. So this is the heat of reaction. That's what H is. Of the products. I don't know why I said products instead of products. Minus the heat of reaction. Oh my gosh, my dog is going crazy upstairs. Of reactants. And we're going to either get a positive answer or negative, and that will tell us the type of reaction that we're going to be working with. So that leads me into the next slide, which is talking about types of reactions, right? So we have two. We have endothermic, and we have exothermic. Endothermic, heat is absorbed, or we can think of it as heat is entering the system. Endo, enter, right? So it is a product. It's going to be on the left side of our equation. And whenever we have an endothermic reaction, our delta H is going to be positive. Okay. So when we have something entering, we also have something exiting. So exothermic. So heat is released or heat is exiting, right? So exit. Heat is a product. It is on the right-hand side of our equations, and our delta H is negative, right? We're expelling heat. We're getting rid of energy. This can also be thought of as a spontaneous reaction, so it occurs on its own. Once it's initiated, once it's ready to go, it's going. You can't stop it, and our entropy is going to increase in this case. Excuse me. All right, I think we have one more slide left for lesson 2, and then we're going to stop there. So the next one talks about table I. So this is on page 5. I had to look at my reference table. In the reference table, table I. And look at this. Let's take a look. 298 Kelvin and 101.3 kilopascals. So this is not quite standard temperature, but this is standard pressure. And if we notice here, delta H is measured in kilojoules. Kg is kilojoules. So this table just shows us a bunch of different reactions, whether it's formation reactions, single displacement reactions, double displacement reactions, or decomposition, and the heat required. If you notice down here at the bottom, it tells you that the minus sign means it is an exothermic reaction. So delta H is positive, it's endothermic, and delta H is negative, it's exothermic. So how we can look at this is if you see an equation here, so like let's look at N2 plus 2O2. Let me see if this will work. There we go. Our delta H is positive. So we can look at that and say, okay, that's really going to be on the reactant side. Whereas this guy, so this guy here, so 2 carbon plus 3 hydrogen gives us C2H6. That's negative. So that's exothermic. So that heat is being given off, right? So that's really going to be on the product side. And just know that when things have a positive delta H and they're endothermic, they're going to get cold, right? Because they're absorbing heat. And when things are negative and they're exothermic, they're going to get warm or hot because heat is being given off to the surrounding area. So keep that in mind. I think that's the end of lesson 2. It is, and we're going to stop here, and then I'm going to pick up with lesson 3 in a second video. All right, guys? So bear with me.